Okay, so welcome everybody to the 4Developers conference here in Gdańsk. If you don't know me, I'm Mateusz Pusz. I'm working or doing C++ for a living like for 15 years right now, all the time here in Gdańsk. So I'm really happy for that we have a C++ conference here, finally, let's say. Besides doing C++ for living in the company, I also the member of the IT C++ committee, and I spent most of my professional time at Intel Corporation here in Gdańsk too. But for last nearly 2 years, I'm working at EPAM Systems doing the low latency software, and I found it so interesting and challenging that I wanted to share some insights with you. First of all, my clicker doesn't work. So let's try again. Clone. Remove that full screen. Now it should be better. Yeah. First of all, we have to define what latency means and how it differs from throughput. Latency basically is the time needed to perform some action from its origin up to the end. It's measured in the time units, like in seconds, microseconds, nanoseconds, whatever, whichever you like. But it's basically how much does it take to produce some effects from the very start to the very beginning of your actions connected with that. Throughput, on the other hand, is the amount of those things being done in a time. So how much kilobytes can you transfer through the network? How many units can you deliver in a day or something like this? Those two are different, and both of them can be somehow connected to the term performance. And when we are talking about performance, we don't exactly know if we are talking about latency or we are talking about the throughput. What I found strange about latency is that it's totally independent from the throughput in many cases. They have some common domains, but it turns out that if you want to increase latency, you have to sacrifice a bit on throughput or vice versa. It's not that you can have both at the same time. So basically what we are striving with the latency, we basically strive to have the low latency here. And the low latency defined by Wikipedia or other guys is this term that's human unnoticeable delays between something that happened and and that we cannot see the problem with it happening until we get the results. It's especially important for internet connections and the communication stuff, basically in voice over IP or network games, or especially in tradings. That is where the money, in fact, is with low latency. With voice over IP, it's just that if two participants of the call will have a low latency connection, they will have really hard time to understand each other. Yes, but basically this is somehow that's frustrating to talk with someone in being in US via the slow connection. But you can handle that. You always say, well, it is because the connection, and somehow you will manage to communicate with other person. With gaming, it's not that easy. If you die in the game. Yes, you may be the best player, have the best strategy, best tactics, and even the best reflex. But if you have a slow connection, you don't have any benefits comparing to other players that may be worse than you. But this is for fun, yes. And the last one is for money. This is the capital markets. This is what I am doing lately, and I found it really challenging. It turns out that there are so many companies doing that right now, trying to find the money in different opportunities happening in the market during the time, that you have to be the fastest one to gain the money, or more money than the competition. So basically, high frequency trading, this is what I'm working on lately, is a program trading platform that uses powerful computers to transact a large number of orders at a very fast speeds. So what we are using very complex algorithms that try to find out the opportunity to gather some money, to make some money from the exchange, from the data coming from exchange to us. why it's called high frequency? Because we are selling and buying products many times over the day, over the hour even. And we are doing a lot of orders like this. It means that, yeah, if you have some capital of your company, if you are having some money, it turns out that it's common for the high frequency trading domain that you buy and sell goods for more money that you own in an hour or in a day. So basically, you may gain some money, you have to invest a lot of money, and you can lose a lot of money quickly if you do something wrong. Yeah. So basically, how our environment looks like. We have an exchange where all the orders, all the data comes to us. There are a lot of them. A lot of them, people are doing trades, selling goods, buying goods, they want to trade something. We have to find the opportunity there. We have to find seller, buyer, we have to connect them, connect all the dots, find out what instruments can we sell. Sometimes it's not that easy. There may be like 2 buyers to 1 seller or other different connections there. So first we have to first process the data. We have to unpack it. It turns out that it's a text form called fixed protocol. Yeah, I know that it may be ridiculous for the low latency, but even the numbers are encrypted with text form, like the price is passed via text there. So we have to do this processing of the text, then gather the data, find out if it's an instrument we are interested in. Then we have to pass through all the trading strategies we have to find out if we can do money from that actually. And then if we can do the money from that, we have to find out if it's safe for us to try to get this money, because sometimes there may be an opportunity, but it may be not that safe, and we can in fact lose a lot of money for that. And basically, what we get here at the upper part of this graph, we take a lot of data from the network, from the market, from the exchange, and only a fraction of this, only a small part, teeny part, passes all the checks here, all the strategies, all the procedures we have, and only a fraction of those, in fact, create an action, like buy one thing or sell something. And the path from this point to the down point is called the fast path. It's in fact pretty simple, pretty short path of software, but all other software is there just to handle the errors, to listen to the network, to process some things that was not successful here. And this fast path, as the name tells you, has to be processed as fast as possible. How fast do we do? If we do a full software approach, we can trade the order like in 1 to 10 microseconds. It's pretty fast, but if you have like all hardware approach, the thing that I don't do right, in fact, but people claim that they can do it even 10 times faster. How fast it is? Let's think about blink of an eye. Things that we say that doing something in the blink of an eye is a really fast, yes? It's 1/3 of a second. During 1/3 of a second, doing things like in 10 times 10 per microsecond, we can just trade millions of orders in blink of an eye, yes? And consider that something wrong happened. That we have some bug in the software, for example, that some person sitting via the console and trying to find out and do some actions. If something goes wrong, just blinked an eye, yes? You just bought everything, million orders from the network, for example, because you had some bug in the software. And it happened. It happened to different companies, in fact. There was a company, Knight Capital, that in 2012 was the largest trader in US equities market. The market share was like 17% on New York Stock Exchange and nearly the same on the Nasdaq. They had approximately 665 million in cash and different equities, and they traded daily $21 billion. If you connect those two, you see how much money they trade over the day, much more than they are worth. It turned out that in 2012, they had a software bug. In fact, it was more like not the software, but the some delivery things that they uploaded the new version to only a few computers and not to all, and they have different versions and working at the same time. So the computers couldn't agree with each other, and they lost 440 million in 45 minutes. The biggest player in US gone nearly bankrupt and had to be sold for 45 minutes after many years of successful operation. You can read more on the LinkedIn article for that. It was really interesting, and it tells how important it is not only to be fast, but also to be secure and check everything. Make sure that all the errors, for example, are not ignored and verified. Talking about the software, software is in fact not the fastest or not the most important part of the system. First of all, you have to have low latency connection. You have to be connected to the exchange with a really fast connection. You have to be close in measure of the distance, and also so connected with good medium, like for example the air communication. It doesn't go through the wire for many clients. It turns to be a bit faster than doing this via the cable. You have to use the modern hardware, the most expensive one right now on the market. Besides, you have to profile that for the hardware for your specific needs. You have to switch a lot of different things in BIOS, in kernel, in operating system. And then you are ready just to put the software on it. Talking about the profiling of the system a bit. I found it on the SG14 forum that we are basically the SG14 is a study group 14 from ISC++ committee responsible for low latency and performance stuff and gaming too. So one of our guys exactly provided this term, spin pin and drop in. What does it mean? Basically, we don't sleep waiting for data. We do the busy spin all around. And it turns out that 99.9% of time we are waiting for data doing the busy spin. The processor is 100% usage. The fans are just hot and loud really, and we are not doing anything. We are just waiting to get the data. We cannot, because it's really important not only to finish as soon as possible, but it's really important to start as soon as possible when the event comes. Because the input already started, the process started, competition already is processing the data, we cannot sleep. We cannot do context switches. We prefer single-threaded scheduling for the same reason. Yeah, and we have to disable all of the features that are really needed for saving the power, for doing the high performance stuff like multi-threading, multi-processor stuff, or doing the things like C-states just to sleep and do other stuff. Everything of this is good and by default enabled for high performance or saving the power. And for our needs, this is not needed. We have to disable all of it. Pin means that we have to know exactly the hardware we are working on. We have to put our software on a specific CPU, assign the affinity to it, so it's the most important one, deal with interrupts, with memory nodes, and many different stuff. And also there is a drop-in. So basically everything that goes to the kernel is wrong. We have to find some replacement for it. We have to use, if we can do all the communication with user space code without having to go to the kernel mode and back, we win, yes? So basically we're looking for some replacements and doing the software module, software parts in user space instead of kernel one. But this is about the hardware. And today we want to scope on C++ and software, yes? So this is basically, right now, the talk about the software. Hardware is other subject. As I said, it's really important and even maybe more important than C++ and software, but we are scoping on this here. Typically, as I said, only the small part of the software matters here. This is this low latency software, this hot path. And that code as it turns out, it's not executed too often, for example. As I said, we spend majority of our time just spinning and waiting for network. We spend also a lot of time doing some error handling when the order cannot be processed, or our security checks didn't apply, and different stuff. This is not the fast path. But when it's executed, when it is a fast path, as I said, we have to start as soon as possible. So we have to spin, we have to do active wait, yes, and we have to finish as soon as possible to be faster than the competition. It's not that easy, in fact, to do that, as your part of the software is not running all the time on the computer, but is just waiting for the orders, and you are doing busy spins, and all other processes on the computer are working. Your CPU cache, for example, or your instruction cache is trashed. It's really hard to start and finish as soon as possible if your instructions are not frequently or often executed. So they are not cached. It's not that easy to do all those things. But most important here is that you have to have predictable and reproducible. You have to provide reproducibility of the performance. So provide low jitter to the instructions. Every order has to be treated the same. You cannot process like 10 orders really fast, and every 10th will be slower, much slower, because you have to go with, for example, with malloc to the kernel mode to get more memory. Everything has to be equal, and you cannot have those jitter, those pins that in your processing. Multi-threading, really nice for performance, for throughput, but it's the enemy for us for latency. It in fact increases the latency. Maybe it provides you some more processing power, but it trashes, for example, CPU caches above L1, because only L1 is per core. So basically, yeah, here is also talking about, of course, multi-threading that you have one thread per physical CPU core. If you are doing more, you are doing this wrong, yes. But even if you are doing one per core, still you have shared CPU caches above L1, you have shared memory bus, you have shared I/O, you share the network. So all of them are sharing your resources, making it basically trying to making the collisions, trying to log them and share them, make it slower. As I told you, mistakes in this software are really costly. You cannot ignore errors. You have to handle them correctly, and you have to make sure that your software is really functional before you will put it on the market. There are a lot of things happening really fast, and if you screw something up, a lot of companies go bankrupt, basically. So, how to develop the software that have predictable and reproducible performance? It turns out, because this is the question that I'm asked by many developers, it turns out that this is not the most important part here, how to develop something, but the most important part is how not to develop something. Because this is the things that you don't do that makes you program low latency. In low latency, we care mostly about worst case execution time, not some average, not the median, but the worst case. And here is the important bullet also, that's often the task not only for C++ code developers, it's also the task for code architects. The design of your code or of your system determines somehow which tools can you use. And if there is a bad design, you have to choose bad tools, and because of this, then you have to sacrifice some latency. So here are the things to avoid on the fast path in C++. The tools like share pointer, std function, we already mentioned them today a bit on the previous talks. They trade performance for usability. They are really nice tools to use for common usage, but basically they have a lot of issues. They can allocate stuff, then they can have some different things that we'll be talking on the next slides. Throwing exceptions on likely path. We'll talk about the exceptions then too in a few slides from now. And other mechanisms here mentioned are dynamic polymorphism and multiple inheritance, RTTI, so runtime time identification, and dynamic memory allocations. All of those 6 are the things that you should try to avoid while working on low latency software. So what's wrong with shared pointer? I'm pretty sure that most of you know that because it's in our industry for years. It was in Boost, right now it's in the standard. Shared pointer is a tool that provides us shared ownership and has a lot of features. But it turns out that because it has so many features, it's highly overused by the C++ programmers. Many take the shared pointer as the default shared pointer, smart pointer that they want to use, even if they don't want to share anything with others. Just to present you the difference. What do you think? What is the difference here between those two? Yeah, exactly that. So I see you are doing your homework with C++. Exactly. Let's see on the Godbot compiler here. This is the code here. I hope I can do this font bigger. I don't know where it is right now. It's I think that it's somehow I lost the part of the screen. I don't know why, but yeah, it should be somewhere here. Okay, but anyway, this is the unique pointer. It's pretty trivial, yeah. It just allocates probably those 4 bytes here and then delete them, and that's fine. This is like 9 or 8 instructions without the function header here. If I change it to shared pointer, how long the assembly code will be? Are there any guesses? Yeah, it's 10 times more. It's 10 times more. As you mentioned here, we can see here the function calls, new operator for 4 bytes, like in previous case, but also there is another one for 44 bytes, 24, sorry, for allocating the state. We have some, what we have here? We have some locking here done, because we have to be thread safe. And going down here, what's interesting here, we have some virtual function call here. And here, in fact, is another one, but GCC manages to devirtualize it. But if you will make it, you will change the optimization level. Right now I have O2. It will be a virtual function call too. And you'll find here more interesting stuff, like, for example, you will find here, what's left? There should be also somewhere the exception handling part, because we have to handle some exceptions. Where was it? Yeah, here, it is here, yeah, like call the catch and end close and everything. We have vtables generated for of course the variable functions and classes. So this is basically 10 times more assembly code needed to just run the shared pointer in a case where we don't need to share anything, because this is exactly what was in this case. So by default, it's good to not use shared pointer, try to use unique pointers by default, and only if that is not good enough, think about the replacement. And I'm not really sure if a shared pointer should be replacement. I don't like the things like reinvent the wheel, but in case of writing customized shared pointers, I think that it may be worth to write something that you need. Because talking about the shared pointer design, in one tool in the C++ standard, you have different functionalities. You have shared state in order to have the reference counting and also to provide the weak pointer functionality. You have the mandatory synchronization, just because we have right now threading from C++11 and everything that's put to the standard tries to be thread safe. And it's not a customization point, unfortunately. So you always paid for atomic ints, and in fact, see here, you have 2 of those. One of them is for shared pointer, another one is for weak counter. We have type erasure. If you noticed, maybe in a type of shared pointer, you don't have information about the allocator or delocator used for the for shared pointer. It's typed erased. If it's type erased, it means polymorphism. It means virtual function calls. It means being unable to, for example, inline that stuff if you are not able to devirtualize. And if you found out that the latest GCC can handle only one of the two cases with virtual function calls, another one is still a virtual function call. Moreover, if you cannot inline that, you cannot determine what will be run in the next instruction, a CPU instruction. You cannot prefetch it to the instruction cache. And instruction cache for me is like, I don't know, 400 CPU cycles. You can do a lot that time. Yeah, so basically all those features that you have here trade usability for speed, for performance, for low latency, yes, in our case. So this is not the tool that you should use. STD function is pretty similar to that. It also allocates, and it also has type erasure stuff. There are some projects out there that are called like in-place function that you can try to use instead. But for short pointers, I don't know if there are any replacements right now that you could find and use. If you want to learn more, this is just a short spoiler. I had a talk last year, like a talk 90 minutes only about the short pointer, so you can find it with all the details. And let's move. C++ exceptions. They are good, in fact. The code generated by nearly all of C++ compilers instead of not on, for most of the compilers, does not introduce a significant or measurable runtime overhead of C++ exceptions. The only exception here is Windows 32-bit compiler that has different approach to handle exceptions, but I think we don't care too much right now about Windows 32 anymore. So we may say that nearly all C++ compiler doesn't provide you any visible, measurable overhead of exceptions as long as they are not thrown. Yes? If they are not thrown, they are pretty, I would say that they don't cost you. If they are thrown, it's a problem. It takes a lot of time. And in fact, the time that has to be used for exception handling is not deterministic. Sometimes it can be short, sometimes it can be long. So basically, it's not good for low latency projects.
By the way, do you have any, I know, links maybe to benchmarks that show the cost of exception or the cost of actually, because it's kind of hard to write a micro benchmark for new different predictors and things like that. So find any benchmarks that show.
Yeah, basically finding a good benchmark to find out if exceptions are cost you or not is not that easy. In fact, I don't know exact results.
There were some in the SG14 mailing list about a year ago or something.
Yeah, Mark Douglas and Patrice Roy have done work on this. If you go to the SG14 reflector, just search through, you'll find it. It won't take you too long to find.
Yeah, so the answer was just go to the C++ SG14 reflector, and there should be some experiments done by Patrice Roy last year, but I'm not sure if he had the final results from that. I know that it depends from the people that are doing those benchmarks that are specified by the owner to provide results that they want to have. Yes, because for example, if you have exception handling and you do not have any error handling in the other code path, for sure the no error handling will be faster than exception handling. Yes. But if you check every error code, you have an if branch for every error code there in the other code. Then so you have branches, you have the instruction cache mess that needed to handle the errors. It may turn out that in fact doing the exception part may be faster because of the less branches, because of better instruction cache usage, and so on. The most important part here for us is that exceptions cannot be ignored. If you have an error, it has to be handled, or you will terminate. Yes. So basically, this is the part that is important for us in low latency, because if you are going into the exception, it means that something wrong happens. If something wrong happened, it means that you are not going the trade, so it's okay for you to go out of the fast path. And if the error happened, you really want to know about it, because you don't want to bankrupt in 5 minutes. Yeah? They simplify the interfaces of the functions. You don't have to care how to provide the error code and the result from the function at the same time. If you have to return a pair or tuple or optional, or maybe make the argument with reference to the results or error, depending what conventions will you choose. It's easier. And at least in my opinion, that using exceptions make it easier to reason about the code. It's easier to reason about the code only if you will assume that every line of your code can throw. I know that people are saying that's controversial and they don't know how to reason, because if something happens, they don't know how the control flow goes and where it can happen. If you assume that every line of code sooner or later can throw, then it's pretty simple to reason about the code. This is my correct path. This is how it's run when it's correct. When something happens, I have an error handling code here or here or here, centralized in specific places where I know how to deal with the problem, and I just do it. I don't have to carry it with in every place to verify what's the problem, and then try to pass that result to a place where I know how to handle it, like 5 or 6 different functions in a stack trace. And besides that, if you are not allowed to use C++ exceptions in your projects because of different restrictions of your environment or maybe your coding standards, it's not the reason to say that you are writing not exception-safe code. I would say that writing exception-safe code is the most important part right now of writing C++ code we do. In fact, one of the biggest companies in the world, sorry Google, they did this mistake. They decided many years ago that they will not handle and support exceptions in their coding standards. So people are still referring to the Google coding guide where it's written that exceptions shouldn't be used in their code. Some time ago, yeah, it was true that exceptions were not the best because the implementation was in compilers was not the best part and so on. But right now, it's good to use exceptions. And Google cannot switch because their code through the years was not only not using exceptions, they also didn't write exception-safe code. So right now they have millions of lines of code that are not exception-safe and will be a garbage, in fact, when exceptions are enabled. They will not be able to process correctly, and right now there is no power in the earth to refactor the code they have to handle the exceptions well. Yeah, so the comment was just to briefly summarize that if you will ask Titus Winters from Google or other guys handling their code, they will say that right now exceptions are not a problem, in fact, because they are fast, but they still cannot enable them on their code base because of the reasons we mentioned about. Another point here that we shouldn't use on the fast path, polymorphism. This is how simple factory method, sorry, not factory method, template method is being done by famous Gang of 4 book, yes? This is how we are taught to use patterns in our code. I would say those patterns are pretty nice for those higher level languages that they don't know what a standalone function is. If you have standalone functions, you have also other mechanisms like templates in C++. It's not good just to follow blindly all the Gang of 4 books patterns. You can do it better. You can make many different things better than just going with polymorphisms to everything. Observers, factory methods, and other stuff. What's wrong with polymorphism? You have additional pointers stored in an object. If it's bigger, it's worse for the data cache, yes? It's extra indirection. You have to dereference the pointer to get function pointer, yes? As I told you and show you, it's not that easy always to devirtualize the virtual function call. If it's not devirtualized, it cannot be inlined, so it cannot be optimized. And also, there is a problem. If you cannot determine what will be the next function, you cannot prefetch it to the instruction cache. So basically, you have to wait with filling the instruction cache until you dereference the pointer, in fact, and know which function to call. And if it happened that it wasn't run in last few seconds, let's say, then it's not in instruction cache, and you have to prefetch it again, which basically takes time. Instead, you can use like templates, like static polymorphism. This is exactly the same, but here you basically can inline all of the code, yes? This is curiously recurring template pattern, CRTP, being used here. You just provide the setup running cleanout in a child class, and provide this child class as a template parameter to the template base here, templated base, that just uses the setup run and cleanup on cast at this pointer. This is safe, this is fast, and this is predictable and fast performance. Multiple inheritance, another case here. If you have two bases and you want to run their functions, you have to adjust the this pointer, because you know that first argument of every member function call of the class has this pointer, yes? So if you have to run a member function, you have to provide this pointer of C. If you have to run B, you have to adjust the C pointer of this to B. But this is not the worst case. The worst case is where you have this so-called die-mode of the red, yes, where you have the same bases, where virtual inheritance goes here, and virtual in C++ always means the runtime cost. So you have the extra indirection to access data members and many different problems connected with that. So this is basically thing to avoid here. At least as long as those classes that you are inherit from are stateful. If they are pure abstract classes without any state, it's okay, yes, you just treat it as interfaces. But anyway, consider always decomposition before the inheritance. How we are doing on time? I'm pretty short. So, yeah, another part here is runtime type identification, RTTI, yes? This is in most cases when you have to use it, it means that you have some smelly design. You can see here that there is a boo that extends the interface of base, and I saw a lot of cases where the code has to be written like that. So you have to access the boo where you have only the base, yes? So you have to dynamic cast here. It takes time. It's not deterministic also. You have to traverse the tree to find out where is, in fact, the D pointer and so on, and find the error, in fact, if it's not the case you want to cast here.
Is it not the case that dynamic cast will throw?
It will throw if there's a reference here. If it's a pointer, it will return you a null pointer. Yeah. Yeah. If you really need to do this, you may do this in this way. It's still not fun, but it should be faster in most cases, especially on Linux that has often only the one runtime pointer compare. But still, this is a smelly design. Please try not to do it. Dynamic memory allocations. What's wrong with them? Basically, our tools like malloc, free, and operator new, operator delete default implementations that use the malloc free under the hood are the general purpose operation. So what does it mean? It means that it's suited for most of the use cases and it's not good in any specific use case. Yes? It has non-deterministic execution performance. It can go even to kernel mode from time to time to get more memory. Causes memory fragmentation. Yes, over the time. So it makes the system slower because it's harder to find a memory block that matches your size, or even may make the fail of the allocation, even if you have plenty of memory left, because just it's not fragmented enough or well enough to provide you a big chunk of memory you ask for. Besides, we can have memory leaks, yes, with dynamic memory allocations.
In which
Yeah, sure. The comment was that it's bad for the cache performance too. So basically what we can do to fight with that, we can provide the custom allocators that address specific needs. So they are not generic ones, they are handling specific needs. If they are handling specific needs, sometimes they have to be handled properly for those needs. It's not that generic tool that can just be blindly used everywhere. Sometimes they can be even slower if you are using these specific custom locators in a wrong way or in the wrong solution. Typically, they prefetch or pre-allocate the memory, so they have lower number of memory allocations with malloc, and they have to provide some data structures like trees or some free lists to handle that memory later on to provide you the memory when you ask for it. So this is basically how the basic interface of allocator looks. It has just allocate and deallocate functions. From C++, I think 11, the size was added to the deallocate, so your allocator can be more efficient. And with simple using alias, you can make your own basic string work with your pool allocator. Yes, the same was done in C++. I think 11. It was PMR was added to the standard. You have also PMR string for polymorphic allocator that uses the virtual inheritance there. It depends if we will solve your low latency problems, because you have to find out if it was devirtualized or not. It's pretty, in most cases, it can be devirtualized, and then it's no cost, but in some more complicated cases, right now the compilers are not smart enough. So it depends. Pro-allocation basically makes the allocation jitter more stable, and it helps in keeping related data together, so you don't have that big fragmentation. And there's also a nice talk of John Lakos about the arena allocators if you're interested in this subject. Another possibility to fight with this is to have small object optimization called SOO, or so small object optimization, small string optimization, or small buffer optimization. It prevents the dynamic memory allocation for the common case of dealing with small objects. And it basically looks like this, that you are providing some buffer that can be used to store the data if it fits there. So all the strings until the length of 15 plus 0 at the end can fit here without any memory allocation. And alternatively, the data will point to the external pointer allocated with malloc or new. But this is being done basically in all of the implementations. But the problem here is that the SSO size is not defined. You don't know exactly what will be in GCC, in Clang, or if it will not change with the time, because, for example, in case of GCC, it changed. The approach they handle SSO, the strings and SSO. So basically, you can find out that your application is running really nice on Windows and really poor on for example, on Linux, or something like this. So this is not the best part of it. That's why we also use the things like no dynamic allocation at all. We have classes like inPlaceString that I built. You can find it on GitHub, that just have the array of characters of specified size, and you can use it like that if you know exactly the size of small integers mostly that you will be using for your product. So you have like symbol of the order or the instrument you are dealing with, the name of the for example the market maker or the people that want to sell or get the goods, or some other information related to it. So basically, you have guaranteed there is no memory allocation here. How to develop the systems? I have to speed it up, sorry for that. So basically, keep the number of threads similar to the number of physical CPU cores, but try to put your fast path only on one thread. Separate IO threads from business logic. This is exactly what I told you. So basically put those busy spins on another thread that is handling the fast path, so the cache is better for it. Use fixed size lock free queues, busy spins to pass the data between threads. Use optimal algorithms, data structures. Use data locality principle to write this, to provide your data being friendly to your cache. Pre-compute everything that can be pre-computed in the compile time, so you can save the runtime time. And basically, This is true. The simpler the code, the faster it will likely to be. It's that simple. Don't try to outsmart your compiler. Really. Putting force inlines and other stuff don't work in longer case. Compiler really knows what to do to make you happy. Know the things you are using, yes? Language, tools, compilers, profilers, and libraries. Know your hardware. Bypass the kernel, use user space mode, measure performance. And the most important here, the most important implementation, I will say it once again, measure the performance. I can say it even 3 times more. When you're measuring the performance, the most important part here is always to measure the release version. Some time ago, my friend came to me and said, you know, on Linux, I'm much worse with my code than the GCC, but on Windows, I'm better with Mingv. That's also the GCC. It turned out that person assumed that CMake is running with release by default. It doesn't. Prefer hardware-based black box if you can. So provide some hardware, for example, in a network before and after your computer to find out what is the overhead of your system from the very beginning to the very end. We don't have to instrumentalize the code because instrumentation can affect, of course, your system. If it's not needed or not possible to use the black box approach, use the profiler. To use the profiler, preserve frame pointer, for example, like this for GCC. No omit frame pointer because it will otherwise make it really hard to find out what you are doing. Familiarize yourself with tools like perf Linux on Linux or xperf on Windows or vtune. Those are really nice tools to measure the performance. Most of them provide you the flame graphs output that shows you how the performance looks. And learn how to read the assembly code. It doesn't mean that you have to be able to just to write it or to code assembly, but read it like I read it. Yes, you see a function call, see what's the function call. If you see log, it means that something is hanging here. If you see things like virtual function call, it's bad. Yes, that's enough. You don't have to understand every instruction there. This is just example how the flame graph looks. And with that, I'm finished. Do you have any questions? Maybe we are free 2 minutes after, so just a quick questions.
Because you did mention that the virtual distractors are actually probably even the worst offenders. I mean, in virtual classes, since usually the object is called in cache when you're destroying it, so you're calling on a cold cache, you load distractions from also a cold cache, and then you destroy the cold object, so you load it into caches and it's destroyed, so it will never go back.
And the destructor may also not be doing anything, but the optimizer doesn't know that because it's a virtual function call.
Yep.
Old and frankly quite stupid recommendation, make your own distractors virtual just in case. Is also a significant offender. I think I've seen a presentation in which changing one distractor from virtual to non-virtual increased the overall performance of the entire application by 3%. So in case of like cloud applications, it's like millions of dollars for just one keyword.
Yeah. So just to summarize the comment, because I fully agree with it, is that just be aware of virtual destructors, which are really much worse than all other virtual functions you have. Mm.
Because I tried to compare Boost with no RTTI, with flat RTTI, and it wasn't flowers and flavors and sweets.
Yeah. So the question is if I'm using the no RTTI flag in my compiler. No, I'm not using that. I would say that space complexity, because it basically RTTI makes your program, the binary, a bit bigger. Probably it's more a problem for Odin than for me, because I have a lot of RAM to run my application. And in fact, it's in a part of application that doesn't matter for me. It's not important. It doesn't mess with my cache and other stuff. I can handle having the types in my binary. It just don't use the runtime overhead of it. Yes? So RTTI is okay to have them and have it in your application. Just don't use the features provided by it.
At least don't expect it to be fast.
Yeah. Okay. So thank you very much.